Whoever has it, it's last call. Okay, that's fine. Okay, we get started here. I want to try and get through 13.7. Just barely here. I'm watching. Has to be handed in by one.
Oh, well, that's just unfair.
Bar's closed. And I went to NIOSA whenever it was. I hadn't been to NIOSA in many years. And anyone go to NIOSA? Were you there when they close? What they do when they close the beer? No, you didn't see that? So they have a police officer with a whistle standing there, and then he's counting down, and then as soon as it hit whatever it was, last call was 10 I don't know what it was. He just starts blowing away on this whistle, and everyone has to stop in mid-motion, If the beer has not exchanged hands, then anyway, okay. All right, so look, we're gonna get through 13.7 today. We're gonna start 13.8. I'm gonna do 2 more examples in 13.7 of Flux. And to remind you what we have for Flux, there are a couple of formulas. The main one I'm gonna use that look familiar? Somewhat familiar? That's what we use. Where we go? There we go. So that's it right there. And this is equal to surface integral over S of f dot n ds, and then this last one. Okay? And then we had special cases. All right, so we want to get to this example. Find the flux of the vector field f of x, y, z equals 0, y, negative z across the surface S, where S is the part of the paraboloid y equals x squared plus z squared, with y between 0 and 1, and the disk x squared plus z squared less than or equal to 1 with y equal 1. Use positive orientation. All right, so we have two surfaces that make up S. Let's start with just trying to figure out what those are. So let's start with this paraboloid. Okay, it's like a bowl, but it opens out which axes? This one right here. Opens which axes? It goes out the y-axis. All right, so we have this bowl, it's sideways. Everyone see it? Okay, that bowl, and then we have a cap on it right here, which makes this surface enclose a solid, doesn't it? But we're not going to talk about that yet. I'm going to call S1 the surface that is created by y equals x squared plus z squared with our y between 0 and 1. And I'm going to draw this out. It's going to look something like that. And remember, our y-axis is coming out of it like this, right? Coming out of the center. And of course, our z-axis goes up, and our x-axis is coming out this way. So that's the picture we have over there. And if we call this S1, then to find the flux, what we can do first is see, is S1 a special case? So is S1 a special case? Well, if you can get one of the variables explicitly in terms of the other two, then it is. And I believe that I could write y as a function of the two other variables, x and z, right? And therefore, it would be a special case. And I gave you that sheet last time, right? Or does this come out of the notes? This is in the notes, right? has the three special cases. So we are looking at the case which is the bottom case right here. And our F in this, our capital F in this problem is this vector field. I'll put it right here. F is 0, y, negative z. That's our P, our Q, and our R, isn't it? That's P, Q, R. And so what we need to determine before I figure out which formula I'm going to use here, or we already know which one, but how I'm going to orient the signs, is I need to ask myself whether or not the normal vectors for this surface are going to be pointed to the left or to the right from our viewpoint. So we want our normals in positive orientation, which means out away from the solid that they enclose. If it does enclose the solid, positive orientation is outward, right? So the normal vectors that I want are the ones that would be coming out of this surface like this, right? Those are the normals I want to use. Most important thing to think about on these normals is that the y component of these normals points in the opposite of the positive y direction, right? I mean, they're all tilted depending on where you are on this little bowl, but all of their y components must be negative if they're going to point that way. And so I'm going to use the formula the way it appeared, I think, on the printout, which would be this. The flux integral, this one, is going to turn into a double integral over d. Now, what's d? Because S is the entire surface, right? This curved surface. What is d? No, that's our ds. We're switching our integration here from saying over the surface to over d. It's the circle. It's the actual constraints of the two variables that are controlling y. All right, so d is going to be our restrictions on x and z, which we have not addressed yet. All right? And then it's going to be p times the partial of g with respect to x minus q plus r times the partial of g with respect to z, then with respect to area. We okay with that? No questions? No? All right, let's plug some stuff in here. This should be pretty clean. I'm going to get this thing out of there. All right, so this should become equal to the double integral over d of what's p? 0, that's nice. 0 times, and just for fun, what's the partial of g with respect to x? 2x, right? That's what it would have been, okay? Minus q, what's q? Oh, I forgot. Q is y, right? Plus r times, what's r? Negative z times the partial of g with respect to z, which is 2z. We good? dA. Let's clean up. All right, let's clean this up. So this is just double integral over d of 2x minus y. Oh, yeah, sorry, thank you. Negative y minus 2z squared dA. What's that? You want to pull a negative out? Okay, we can do that. Let's see now, can we get some control over our D? So look at D. Go to polar. So what we try and imagine is that we're taking the projection of this surface, right, onto the xz plane. And the reason we're doing xz is because it's a function of x and z. So if you project that onto the xz plane, you should get a circle back there, shouldn't you? So in the xz plane, that circle back there that maps out to that surface has what as its radius? Well, how far out does this bowl go? It starts with y equals 0. That's the smallest coordinate, right? And then the biggest y gets is 1. So if y is 1 in this equation, then that's a circle with radius 1, isn't it? And that's what we'll project backwards. So this should be a circle radius 1. So I should use polar conversion, letting theta go between 0 and 2 pi, and my r should go between 0 and 1. Yeah? Now, what are the conversion identities that I can use here? Like, I can replace what with what here, if I'm going to use the polar coordinates here. I can replace x squared. Anywhere I see x squared plus z squared, I could replace it with r squared. I can replace x with r cosine theta, but not y, right? Not y is r sine theta. It's actually what? Z, because we were in the xz plane. So those are our polar conversions that I'll use. And by the way, what is y? Yeah, remember that because of the way it's written, y is equal to x squared plus z squared, right? If you live on the surface, that's what y is. And we know x squared plus z, this should have been what? Sorry, thank you. This should have been z squared. This should be r squared, right? Understand? So rewrite this now. This integral should turn into, now I can put some limits of integration. How about we go 0 to 2 pi and 0 to 1. Let's pull that negative out, that negative that was in here. And then we have y, right? And what's y, we said? R squared minus 2 times, or plus, because I pulled the negative out, plus 2 times, what's z squared? Well, it's this squared, right? So r squared sine squared theta. And then r, right? R, we have to have r, because we went polar, dr d theta. Is that okay? Question?
No, we were saying that if during the special case,
do you not do the square root 1 plus the partial?
We did this special case earlier. I think you might be confusing it with surface area.
oh yeah,
There was a special case for surface area where we could convert the magnitude of the cross product of the partials of r. I think you're confusing that with this. Which, if you've been doing your homework and you're trying to keep up with this, which I know some of you have been doing, this can all start to get pretty confusing because you get a lot of formulas, a lot of different things that are happening here. You have to know what you're supposed to do. It's not just like grab a formula out of a bag and go, yeah, I'll use that one. You know, looks right. But you see why on the final I don't really even have to ask you a question about a double integral, right? I mean, I don't need to ask you a problem on your final that's going to be like, hey, you know, do this double integral and it converts to polar. I just can ask you something like this and it'll kill all those birds with one stone, right? So it's like 5 or 6 birds with one stone. All right, so now at this point, I don't think I'd want to do the rest of that, but it would be pretty easy to do, right? Can I say easy? I mean, relatively speaking, the r goes through, and then you can integrate everything with respect to r. You could also factor an r cubed out and split them. But I'll tell you, if you work this on your own, you should get, as a final result here, negative pi. Let me double check that. Yeah. If you work it out, you should get negative pi. Okay? Now, that's just S1, right? S2 was that other piece, and we have to look at that also. So this was for just S1. All right, so let's look at S2. Now for S2, we had just this part, right? It was that circle that capped off the paraboloid thing. It was like that piece right there. And could I go about this the same way? I could. Can I look at this as being like y is a function of g, or sorry, y is some function of x and z? No? Which part? The disk is an inequality, I agree with that, but do you agree that this disk lies on a plane? What plane does that lie on? It's parallel to the xz plane. It's actually y equals 1, right? Isn't that what it is? And that, you could say, is a function of two variables, x and z. They just don't appear there. And then you could go to the shortcut, couldn't you? It's just that your partials are going to wipe almost everything out. That's one approach. I'm not going to do that approach. I'm going to do something a little different. It's faster, and I think you'll appreciate it. All right, so look at this. Let's take a look just real quick. Because it's a plane, what can you tell me about the normal vectors that are pointing off any point on that plane? Tell me about a normal vector, a unit normal vector that would be coming off of that. What does it have to look like? Any normal vector. A unit normal vector.
1, 0, 0.
Close? Those are all pointing out the y-axis, or the y direction, right? 0, 1, 0, right? All normal vectors would look like that? Do you agree? Yes? Okay. That's only because of the way it's oriented. So instead of using the formula we just used in the shortcut, I'd like for us to entertain this for the first time. I have not shown you one of these yet. That's why I'm doing it. Okay, this right here, and we're going over S2 right now. I'm going to use the formula that looks like this. F dot n ds. So that is one of our formulas. What happens is this ds vector s turns into n ds, where this is surface. All right? The value of this formula is that if you know how this normal vector behaves, especially if it's always the same, then this dot product becomes very easy to compute. So what would happen if I take my vector field, which I erased here? My vector field was 0, y, negative z. If that's my vector field, if I dot that with this vector, what's going to come out? So dot this. Take this and dot this. Just the y, right? That's the only thing that comes out? Agreed? So this turns into this y ds. Are there any questions on where that came from? No? Because I'm not writing it down. I just want to make sure everyone's clear on this becomes y. And then, because you're on this plane, right? Because this circle is on this plane, y'all see the plane I'm talking about? The y coordinate was always 1, wasn't it? So y is 1 always when you're on S2. So this just becomes double integral over S2 of 1 ds. And what is this? This is a special formula when you have a 1 in here. This is the area of S2. That's what this represents. And S2 is a circle, right? S2 is a circle. And what is its radius? 1. So it should be pi r squared. So this should just be pi. With no work. You see that? With no work at all. So can we answer the final question? What is the flux over this surface, the entire surface? It's pi, negative pi plus pi, which is 0. So the flux turned out to be 0.